back to our lecture on models of quantum computation. So this is the menu for today. I already talked about teleportation. Where is my stick? Last time. But I want to go over it again in a little bit in greater detail because it's a very important protocol for us. And then we begin with our first model of quantum computation. It's a circuit model. It's kind of the standard model of quantum computation. And I want to motivate it through reversible classical computation, and then explain what it is made of, what the individual components are in these circuits, and then I talk about two quantum algorithms. One is a toy algorithm that's Deutsch's, and this is just to make a fundamental point of view, that you can do things with quantum circuits that you cannot do with classical circuits. And then I want to talk about Shor's algorithm. Shor's algorithm is a quantum algorithm with an application. So it has everything you need. It has much improved scaling. I mean, it's much more efficient than classical computers for that problem, and that is significant in this case. Yeah, there's an application, even if it's not a nice application, but it is. It shows you that quantum computers are something to be reckoned with. Okay, so that's the plan. It's a lot for today. I don't know if we are going to get there. But let's get started. So I want to begin with teleportation. And if I didn't already say it, I want to say what a qubit is, because this is kind of our unit of quantum information processing. So a qubit is a state in a two-dimensional Hilbert space. So we have a basis for that Hilbert space. We call these basis states 0 and 1. And then all the states we have, all the pure states that is, they are superpositions of two basis states. Yeah, and that's the qubit. And then of course we want many of them, and many qubits we describe through the tensor product Hilbert space construction. Yeah. So if you have one, you know how to get many. I mean, in theory. Okay, and then there's a blob sphere picture, and maybe that is also of interest to you, and it is quite useful. We will use it today. So what you see here is that quantum states, pure quantum states, they correspond to points in the sphere. So you also have states inside the sphere or inside this ball, and these would be mixed states. Okay, if you want to make it a little bit more, how should I say, precise what this picture means, what you've plotted here as the x, y, and z coordinate are the expectation values of the Pauli observables x, y, and z. So when you plot the triple of these expectation values, you get a point in this three-dimensional space, and you'll find that all pure states will lie on the sphere and the mixed states will lie inside. And outside are not allowed quantum states, because positive semi-definiteness would break down. Yeah, okay, so that's what the qubit is. And so now with that, let's go to the teleportation protocol. So let's first talk about what it does. So suppose you have two parties, like, I don't know, Alice here and Bob here. They can be very, very far separated in space. And the idea is now, or the task is, to carry a qubit from here to this other location. And one way you can do it is, well, you just take the qubit, it has some physical carrier, say an ion or an atom, or lives in some Josephson junction array, so you take it with its physical carrier to the other location. That's a trivial thing that you can do, but the question is there something else that is of interest? And one such thing that is of interest is you use teleportation. and then you do something different. You will not take this thing with its carrier and move it along, but what you do instead is you prepare an entangled state between the two parties, like so that one system that's entangled lives on this side of A, and the other particle lives on the side of B. And now you have two particles at A, namely the state that you want to teleport that may be unknown. Anyway, I don't know if you can see this. Anyway, so this represents my one particle, and now I have another particle that's coming from the entangled state. And now I measure these two particles jointly in the appropriate basis, and what comes out of that is you will have teleported the unknown state that you held here, or maybe you knew it, the quantum state that you held here, to the other side. Okay, so all that you have to communicate now is the outcomes of that measurement. You were measuring these two particles in a suitable way, and we'll talk about it. So there will be outcomes, and those you need to communicate. And depending on the outcomes, there will be a correction operation over here. So that is what you do. So it gets you the quantum state from one place to the other, but all that is ever communicated is classical information, 2 bits of classical information, and you're also using up an entangled state. You can use this only once. If you want to teleport again, you must make that state one more time. Okay, so this is what the protocol is about. And it exists in all sorts of variants that are interesting for computation later. Okay, so I want to explain it. I mean, it's a simple protocol. It lives in an 8-dimensional Hilbert space, so you can compute everything about it using Bell measurements. Okay, let me just check. I'm a little bit surprised about the order of the slides. Yeah, forgot to delete that slide. Okay, yeah, let me delete it right now because we will not need it. Okay. I hope that was a good idea. Anyway, now it's gone. Okay, so let's begin with the protocol. So I will be filling in the details of what I already said. Yeah. So here we have party A, and here we have party B, and that can be very, very far away. I mean, the neighboring city, the moon, whatever you like. It doesn't really matter for the protocol. So here, the state is in existence at party A, and who knows who prepared it, can be known or unknown. And at the end of the protocol, the state will come out on the other end. And that is not in contradiction with the no cloning theorem, because at the end of the protocol, the state is no longer present here on the A side. So that these two particles will have been measured. Yeah. Okay, and it uses a Bell state. So the entangled state I spoke about is a Bell state. Yeah, and we will find out shortly what all of this notation means. Okay, so this is prepared, and of that Bell state, either party gets one copy. Okay, and so now on the side of the sender, the state to be transmitted and this extra qubit, they are measured in the Bell basis. So we will find out what the Bell basis is. Okay, so it's the second thing that happens, and then the measurement outcomes are transmitted to the other side and conditioned on the outcomes of these measurements. Correction operation is performed. And then the claim is the state that went in over here comes out over there on the other end. Okay, so that's the protocol. So you can transmit a quantum state without carrying it over. Good. And so that is what we want to talk about now. So here is explanation of what is what. So yeah, so the Bell states form an orthonormal basis, but before we get into the basis, let's begin with the first Bell state. That's the one that goes into the protocol here. Okay, what is it? It's a 2-qubit state like this. So either both spins are either up or both down. So you have superposition of these two possibilities, and the relative phase is +1. Okay? So this is the first Bell state that we deal with. So another Bell state you may also recognize, this is what we call here B11. So there was the spin singlet that we talked about when we discussed Einstein's spooky action at a distance, or the correlations that follow from entanglement. Okay, so here it is different in two ways from the first Bell state, namely it has a phase of -1 now, relative phase of -1, and the two spins are oriented in opposite ways rather than parallel. Okay, good. So this is the Bell state that occurs here in the protocol. This is the Bell state you already saw, and then you see two more here. And yeah, so how do they differ? And how are they the same? So you find two of the four Bell states have a positive relative phase, namely this one and that one, and two have a negative relative phase. So one label here is for the relative phase, and that's the second label. So that label is 1 when the phase is -1, and it is 0 when the phase is 1. So also you have two states here in which the spins orient in parallel, that is here and here, these two. And whenever that happens, the first label is 0, and when they anti-align, the first label is 1. So this is how the labeling comes about. And now that you have given these states, you can easily convince yourself that they form an orthonormal basis. Good. And that's the basis in which you measure over here. Okay? So, so now we have explained almost everything about the protocol except what this is. Sigma stands for Pauli, but we want to know a little bit about the labeling. So next thing we care about is that there are certain relations between these Bell states. So we can consider B00 as our reference state, and then we can obtain all the other three Bell states by applying Pauli operators. Yeah? And furthermore, we can choose to apply these Pauli operators on either side. Yeah, it doesn't matter where we apply them. And this will also be of relevance. Okay, I mean, so these signs here, they mean proportional. So in this case, we are not caring about global phases. Yeah? If you would care about global phases, then the phase might be different whether we apply it here or there. But, okay, let's not care about global phases for now. Good. Okay. Yeah, so that's an important property that we will use. And so these sigma, so the fact that you can get from one Bell state to the other by applying Pauli operators, this will be relevant for the protocol, for the correction operation. Yeah, so why does it not matter where you apply these Pauli operators to which of the qubits? And that comes out of the relation down here. So for all the four Bell states, they have the property that if I apply a Pauli operator sigma, tensor sigma, same Pauli operator on either side, then the Bell state is going to be an eigenstate of that. So I get the same state back up to possible phase. And now I can, and that holds for sigma x, sigma y, and sigma z, holds for all three of them. And now you see, so we can take this relation and multiply it with such a sigma, say on the side A. So sigma squares to the identity. So if you multiply it, this thing goes away, but it appears on the other side. And that is the reason that these relations hold, that it doesn't matter where you apply the Pauli to get from one Bell state to the other. Yeah? So in these relations, that's what we call a stabilizer relation, and the stabilizer formalism, of which this is part, will be very important for this course, and we'll talk about that next week. It's just the first time you see it come up. Now we are going into arguments. So the purpose is to explain the teleportation protocol. As I said, this is all in 8-dimensional Hilbert space, so you can do it in any way you like. You can do it in the matrix representation, but we want to explain it a little bit here. Yeah? So we need to establish more properties of Bell states, and then the protocol will be rather easy. Okay, so let's begin with something that we saw earlier. So here we have a Bell state B00 appearing in the protocol, but we don't know this guy very well yet. So what we do know is B11, yeah, the Bell state with anti-parallel spins with negative relative phase. The spin singlet, we talked about that. And the one thing that we learned about it was that if we take such a state and then measure one particle of it in a certain basis that contains this state psi here, so this is the projector onto psi. When we do that, what we get out is that state on the particle that's being measured tensored with the perpendicular state, the state that points in the opposite direction on the other particle. So that's something we talked about earlier. Okay, and now we want to know what this does to what follows from that for the Bell state B00. Okay, so that's a state that occurs in the protocol. Okay, so we are using the fact here that we can go from here to there by applying a Pauli operator sigma y. And we can do this on either particle, so let's do it on the particle that is not measured, not physically measured. So is sigma y applied to B11. So now I can exchange the order of the operations, yeah. So this guy lives on a different particle than this, so they trivially commute. We can push this thing through. And then we know how this projector acts on that state, that's what we have established before. So it gives us, well, the state in which we measured, and it gives us the perpendicular state on the second particle, but we still have this Pauli flip hanging here, and that is applied to the perpendicular state. So in this state occurs a funny state that I call psi tilde, and that's the perpendicular state of psi, then with a Pauli flip sigma y applied to it. And so just to make my notation a little bit simpler, I'm giving that state a name, and that is something we have to argue about. But at any rate, the upshot is this. Yeah. So when I so I'm coming here from this line. I'm multiplying this line from the left with psi or bra, with the corresponding bra. That removes this factor, and so this inner product is what I remain with. So I measure in this state, having a Bell state to begin with, and this leaves psi tilde on the other system. So that's a relation that we want to remember. This is what we just found. I have just copied it from the last slide, and now let's make it even more general. So we had this for B00, we had it for B11, so now let's write it for either of these 4 Bell states. Okay? And so we know Bij is just our reference Bell state B00, and then some suitable Pauli operator applied to it. And yeah. And so now we can have this Pauli operator act on our state psi on the left. Okay, and so so we can use this relation with that state, and so this gives us sigma ij applied to psi tilde on particle S. Good. And yeah, so this is now, we need to take one more step. So we take the Hermitian adjoint of this. So to flip things around, we have the cat here, we want the bra. We have the bra here, we want the cat. Yeah, so we apply the Hermitian adjoint to flip this around. Okay, we do this on both sides. So on the right hand side we have that, and so now we get this upon taking the Hermitian adjoint, and this will be our third relation that we remember. So this is what describes the first measurement. Yeah, so you have a state here, psi on system R, or that will be one of the particles at A. So we will get to that shortly, and we are performing a Bell measurement on it. And the significance of this will be that this acts like a projection on the particle that is not physically measured. Sorry, there was no state provided to. Yeah, it acts like a projection, effectively, on that particle. So there's one more relation that we need. So we had this state psi tilde. Remember what that was? It was taking the one orthogonal state that we have in our two-dimensional system, and then applying a Pauli operator sigma y to it. If we do this twice, this operation, then we get back to the state we had. Okay, so that are you?
I'm thinking on the two Phase vectors multiplication on the Phase space. Like,
yeah.
Okay, you will get the same state back.
Yeah. So the easiest way to see it is to use the blob sphere picture.
Yes.
So what the tilde does, it takes all the expectation values of x, y, z into their negatives. That's the first thing that happens. Then applying sigma y is a 180-degree rotation about the y-axis. So the expectation value of y remains the same, and x and z, those expectation values are flipped again. They flipped the second time. Yeah, so if you look at those two operations together, then overall the expectation value of y is flipped and x and z remain the same. Yeah? Only y is flipped, and so if you do this thing twice, so y is flipped twice, also remains the same. Okay, so now we'll remember that relation too, and now we can begin using these relations. Okay, so yeah, so now we come to the labels. So, so we begin with this part of the protocol. So we have this portion here. So we have the state psi that's going in, and it is measured in the Bell basis. So that's now the part of the protocol that we talk about. And now also note that there are labels here. So the party A gets particle labels A, and party B gets particle label B. And because there's two qubits now, we call them A1 and A2. And so now we apply this one relation that we had, so that involves the bra of a Bell state and the unknown state ket on the first system. Yeah, so this relation we use now, and we apply it as follows. So what was a general system R here, unknown state, is now system A1. And what was S here is now system A2, so the other particle. So we specialize to these and use this relation. So here we have a state and projection on a Bell state applied to it, and this is the same as a projection on the state psi tilde on the second particle. Okay, so when we know that and apply it here, then we find that this circuit simplifies to that circuit. So what's there? So the Bell state we didn't touch, all the stuff down here we didn't touch, but the measurement has simplified. This is now, or the projection into Bell state Bij becomes now the projection onto the state sigma psi tilde. Okay, so that's the first simplification that we found. Okay, so the first qubit is now completely out of the picture. Yeah, and we are now effectively doing this projection on a Bell state B00. Yeah, and you know this from our earlier discussion of the Bell state 1-1. When you measure a Bell state in one particle of a Bell state in this way, then you will be projecting also the second particle. Yeah? Good. So now let's see this with the formulas that we have derived. So now we are using this other formula. So what happens if we project a particle? This is exactly the situation that we have now. You project one particle of a Bell state into something, what do you get on the other side? So this is what we have derived. And also, we use this other rotation that psi tilde tilde is psi again. Okay, so we begin on that circuit and apply this relation with, so here we have the labels RS, and here we have the labels A2 and B, so we need to talk about who is what. So we apply this relation now with R being A2, so this is the projection that's going to happen, and S, the other particle being B. So this is where we have a system remaining, and we use this relation not for psi, but for psi tilde. Yeah, it holds for all psi, so for all states, so that's okay. And so when we do this, we get, so what comes out of this relation is that psi gets a tilde on it, so it already has a tilde, so it gets a second tilde on it. And so that's what we find, yeah. And yeah, so these Pauli operators, we also saw this earlier, they get mapped to the other side by those stabilizer relations. So what happens is the following. So we have psi tilde tilde, we have this Pauli operator applied, and then we have this other Pauli operator waiting there. So that was the correction operation in the protocol. And now you see that these two correction operations cancel one another out up to a possible phase. Yeah, Pauli operators, if you correctly, if you choose them permission and so on and so forth, they would square exactly to the identity. Sometimes you have different phase conventions, but either way, those two cancel each other out up to a possible phase. So this goes away. And now we have this other relation that psi tilde tilde is psi. Okay, and so the circuit simplifies to this. It's just the state psi transmitted. And now we begin with the first model of computation that we're going to discuss. And it's kind of, as I already said, it's the most widely used model. Most people prefer to think in this model. Yeah, and so it is worthwhile reviewing it here in this course. And moreover, the two models that we are going to discuss in detail, that is quantum computation with magic states and measurement-based quantum computation, these models have a close relation to the circuit model. I mean, so there's a mapping that goes between all these models, and yeah, so that's why it's good to review the circuit model first. I mean, that's everybody learns who starts out in quantum computation. We will also review a computational model, but very briefly only, that's rather different, and that's adiabatic quantum computation. So that's, if I'm sufficiently fast today, is what we'll do tomorrow. We'll pay not too much attention to adiabatic quantum computation in this course. We only mention it because it is rather different. Good. Okay, so that's what we're going to talk about now. So the circuit model. So, and you will see lots of diagrams like this. So maybe it is worthwhile trying to parse what's on here. So the horizontal axis is something like time that's progressing, and the vertical axis represents the quantum register. So that's a bunch of qubits. So initially, these qubits are prepared in a fixed state. So it will always be the same. So in quantum computation, there is no variation in the initial state. The initial state is always the same. For example, all qubits being in state 0. Yeah? And you need nothing other than that in terms of preparation in the circuit model. So then comes the varying part, and this is a bunch of quantum gates. All that needs to be said at this point is that these quantum gates are all unitary, and yeah. So, maybe let me say one more thing. Unitary evolution means generated by a Hamiltonian, and you know that to get particles interact in a quantum way with one another is kind of hard, not impossible, far from it, but it's kind of hard, and so therefore you want these gates to act on as few qubits as possible. If you have them interact only on one single qubit at a time, this will not suffice, because then these particles will never interact and you are not exploring much of the Hilbert space. So you need interaction. You need groups of qubits, of at least 2 qubits, interact, but it turns out that's also all you need. You only need 2 qubit interactions. And we'll talk about that in some detail later. But that's the variable part. So the quantum algorithm is encoded in this sequence of gates. Yeah? And then at the end, you have measurement, and measurement can be local, 1 qubit at a time, and you're not losing anything if you measure in a fixed basis. So that's the circuit model overall. And so what is required is to figure out what's needed here. But we will not go to that directly. We will make a little bit of a historic remark. And where did that all come from? So this was a discussion in the 1960s and 70s. So the question then was whether there are fundamental limits to the energy consumption of computation. Yeah? So this was by Rolf Landauer, IBM. So you'd think that at IBM they would care about such questions. So, and Landauer had the idea that what costs energy in computation is erasure of information. And so he came up with this formula. Yeah, you see. You have a certain entropy. The ln of 2 comes because it's a 2-state system. Boltzmann constant here. You know this is an entropy, and he postulated, reasoned, argued that the energy that is required for the erasure of 1 bit of information cannot be smaller than this. Yeah, so it was a kind of contested argument, or it was, I mean, in his paper he describes 2 models in which this is true, and then much later a proof from first principles was given. So it is indeed correct. Yeah, and so he thought, okay, in every computation you need to erase bits. You need to clear your memory to have it available for further processing. So yeah, so there's no way around that bound. Yeah, so that gives you a minimal amount of energy that you need to spend if you want to compute. So he argued. About 10 years later, somebody in Landauer school, Charles Bennett, was thinking about, okay, so what is the, maybe there are some computations that can be done in a reversible fashion. So what would they be? You can do everything in a reversible fashion. So let's now look into this at some detail. Yeah, and kind of, especially the first part of what I now say will retrace what the discussion was. So yeah, so we have these, let's see, is it a function? Yeah, it does function. So, so we have these gates, we have AND and OR, and we have NOT, and the AND and the OR, they are such that yeah, there's fewer outputs than inputs, so we are losing information when we run them. Yeah, and so then presumably Landauer's bound would kick in. So by the way, the AND gate and the NOT gate together, they are universal, so this is all we need, but we have this non-reversible thing here. Okay, and so yeah, this is what a classical circuit would look like. We can, because we have a relation here, we can even remove the OR, and we can just use the AND and the NOT. Okay, but what we now do to make the computation reversible is the following thing. Okay, I think that was not strictly necessary, so because the NOT is reversible, so okay. Anyway, I replace it here by a controlled NOT, where we use a bystander particle, and then we can simulate the NOT via just kind of putting a bit with value 1 into that bystander particle. The problem, however, is that it sticks around. We have wasted memory doing this operation. We can do the same with the AND gate. We replace it by the so-called Toffoli gate. So what is this thing? So this Toffoli gate is a gate, it's a 3-bit gate, and it uses 2 controls, B and C, and 1 target. And so what's happening is that the target bit is flipped only if both of the control bits are in state 1. Yeah? So then it is flipped, otherwise not. And so now you can use this Toffoli gate to simulate an AND in the following way. So on the top bit you put in a 0, and then, well, after you have passed the gate, you will have the B and C in that slot. The difference with the AND gate is you have the input still sticking around, so that's why it's a reversible gate. You're not losing the input. But again, that costs memory. You have these half-computed things lying around, yeah, and that wastes memory. So that alone doesn't solve the problem. So we need another trick. And this trick comes now. Okay? So this is some circuit in this fashion that simulates AND gates and NOT gates using these more complicated things and certain ancillary states that facilitate these gates. Okay, and so without loss of generality, let us look at a circuit that produces 1 bit of output. And so now we do the following. Yeah, so this bit of output, say, is, what would it be? Say it is produced here. So let's say that this is the bit of output that we really care about. So what we now do is we add another bit, prepare it in state 0, and we use the C0 to copy that bit. Okay? So now this is going to be our computational output. So far, basically, I think this covers the discussion that we had. So we have our bit of output now, but we also have all this junk lying around. And so that was now Bennett's idea. So, and you know, when you see it, it is not very complicated, but that's hindsight. You still would have to have had this idea in the first place. Okay, so the next thing, or the last thing that's being done, is that you do this circuit in reverse. Yeah, and so how do we do the circuit in reverse? We do the last gate of it. So these gates squared to the identity, so the gate is its inverse. So we do that gate and reverse it. So next comes this C0 down here. We reverse it, and then we reverse the Toffoli. Okay, and then we have exactly what we started with. Yeah, so this bit started in state 1, this started in 0, this was started in the input. So we are giving the register back exactly how we found it. Yeah? So this was the reverse circuit. Yeah, so the reverse circuit uncomputed all these intermediate outcomes. Okay? So the upshot of this is that you can perform any computation in a reversible fashion. This was the clever thing in this construction, this uncomputation of all the intermediate outcomes. Yeah, and this is classical computation, and the reason that we are reviewing it in a course on quantum computation is that it puts a focus on reversible gates. I mean, Bennett and company, they were interested in it from the perspective of energy consumption, but a quantum person may think, oh, you can compute with reversible gates, unitary gates, or unitary operations are reversible. So maybe you can compute with unitary operations. And yeah, and that is kind of the connection to the circuit model. Yeah, so here's, in fact, a slide with that very conclusion. Okay, so this is the reason why we talked about the Bennett trick here in a course on quantum computation. Yeah, it puts your focus on reversible operation, and reversible operations in the quantum world are unitary operations. This course will have a lot to do with measurement, and measurements are not reversible. Okay, so conceptually this is a kind of a different animal. Okay, but with reversible operations we stopped out, and this is how people got thinking about the circuit model of quantum computation. Good. Okay, so now let's get back to quantum. Yeah, back to quantum. So end of motivation, we are now back with this computational model. And so remember that circuit with these boxes, we now fill in these boxes. So the first notion, this is the definition of the notion of universal gate sets. Yeah, so a set of gates is just a bunch of gates put together, or well, just a set of gates. and they can have a particular property, a property that we want in quantum computation, and that property is computational universality. So let's define it. So we say a set of gates is universal if, for any integer n, all unitaries in the special unitary group 2 to the n, so this is the unitary, special unitary group that applies in the case of n qubits. So any element in that special unitary group can be arbitrarily closely approximated through circuits with gates from that set and from only that set. Yeah, so I have a bunch of gates, and I can, by concatenation, I can make circuits, and what I want that these circuits get me anywhere in SU2, SU2 to the n, or at least arbitrarily close to anywhere. Okay, and that's kind of the standard for quantum computation. If you cannot do that, then you have to argue very hard that your device is useful. Yeah, so this is really what you want to achieve. And I give these examples without proof. So I give you two sets, two universal sets. So apart from the C0 gate here, which I defined below, you remember this from the homework assignment. Even though I believe in the homework assignment the angle was fixed, here you have all angles. Okay, so these two gates, they don't couple. Oh, the label below is on which qubits these gates are. So this is for all qubits I and for all pairs of qubits ij. Yeah. Okay, so this is local, acting at one qubit at a time. This is local, acting at one qubit at a time. So these do not generate interaction. So you need something else. And it turns out you need only one other thing, and that's this controlled NOT gate. So this is also what had the classical counterpart. I think we've already seen what it does, and so let's write it down one more time what it does. This entangling gate. So it has so this is the explanation in a particular basis, so-called computational basis, so the eigenbasis of sigma z, Pauli phase of operator C. Okay, so we first explain what it does on the basis states. So you have a basis state A can be 0 and 1, basis state B can be 0 and 1, and so what it does, this is qubit down here, it's called the control, it just stays in the same state, but this qubit up here is flipped conditionally on what B is, or in other words, the value of B is added to the value that's already in it, modulo 2. So this symbol here, the plus in a circle, this is addition modulo 2. Okay, so that's what happens. And then the quantum mechanics is linear, and once you have defined it for the basis states, then you know what the gate does in general. Okay, so this was one explanation here, an equivalent notation. So the first qubit is the control, that's the lower qubit here, the second is the upper qubit. So if the control is in state 0, then nothing happens to the target. But if the control is in state 1, then the target is flipped. Yeah, same thing. So that's the entangling gate that appears in that set. And so there's the other gate that we still need to define. I think you know it from homework assignment though, and that's the Hadamard gate. And as a matrix, in the computational basis, it is written like that. Yeah, it's a unit. You can check that it is unitary. H dagger H is the identity. It further has a property that is squares to the identity, so it's its own inverse. And interesting to know is that it takes eigenstates of Z and turns them into eigenstates of sigma Z for now, and turns them into eigenstates of sigma X, and the other way around. So it flips the Z and X eigenbasis. That's what the Hadamard does. Okay, so with this explanation, this is fully defined. Yeah? So these are rotations about the z-axis, all angles. That's the universal set of gates. So out of those, you can make any unitary in these larger Hilbert spaces, in all n-qubit Hilbert spaces. And I give this result without proof. So it's a result maybe from before 2000. It's a very old result. Okay, so that's the first set, first universal set. So we don't need all rotations about the z-axis. We can fix it to one angle, and that angle is pi over 4. Now spin 1/2, so pi over 4 becomes pi over 8 here in this exponent. Yeah, so that suffices, and that is very important for fault-tolerant quantum computation. We will talk about fault tolerance here very, very briefly only, but we will mention it. And the fact that this is enough for universality is important for fault tolerance because that gate is comparatively easy to make fault tolerantly. General rotations not. General rotations are very, very hard to make fault tolerantly. So that is important for the theory of fault tolerant quantum computation. So there's two more things to discuss in this class. There are two quantum algorithms. The first is Deutsch. This is from 1985. And is kind of just makes a point of principle. It's not a quantum algorithm that's of any use. It's just kind of to make a point. And the second algorithm, that's Shor's, that's from 1994, and then that's an algorithm with a practical application. Okay, so let's begin with Deutsch. So it's just to point out a fundamental distinction. And so the task here is maybe a little bit contrived. So consider the following situation. You have a function that goes from the binary numbers to the binary numbers. There's 4 such functions, and you want to know, you don't want to know all about the function, you just want to know if it is constant or balanced. Yeah? Constant means constant for both inputs, has the same value, and balanced means it has different values for different inputs. You don't care for which input it has 0 and for which input it has 1, but you want to know, if it is balanced, it means the value is different. Okay, so and the task is given a function, such a function, find out which one it is. And here is how the function is given. It is given as an oracle. So you have a box and you can throw inputs at this box and it will tell you outputs, corresponding outputs. So that's what given to you. So classically it turns out you need 2 oracle calls. If you just call the oracle once, well, it gives you the function value, and that doesn't determine whether the function is constant or balanced, so you need to call it a second time. It turns out that quantum mechanically, 1 call suffices. So there is a fundamental distinction, even if you don't care about this particular problem. There's a fundamental distinction between the quantum and the classical case, and in 1985 that was a point to make. Yeah. So we are using an oracle in either case, and this is what the oracle does. So it takes 2 bits of input, and let's begin here. This is what we really want to do. So you have the input A, on which you want the function evaluated, and you have a bystander qubit or an ancillary qubit. And now you feed this to the oracle, and what the oracle does is it gives you the input back and then puts in the second register the output. Okay. And so that's kind of what you want, but we have to have this thing to make it, because we need to explain that the oracle is meaningful. It does something that can be done, and so if you would just put in the input and get the output, could be the constant function, and the constant function erase this information, so that couldn't be done reversibly. Here everything is unitary, so you want it at least be reversible. Okay, and so the way we get this reversibility is this. We have two registers, the one we care about and another one, and what the oracle does is it keeps the register first register what it was, and then to the second register it adds modulo 2 the function value to whatever was already in that register. You can easily convince yourself that this is a reversible operation. In fact, this operation is its own inverse. Okay, so you get this is reversible, and now you can specialize the second register to 0, and then this oracle gives you what you want. Yeah? You get the function value out, and you also get the input back, so to be reversible. Okay, so that's what the quantum oracle does. And now you query this oracle in superposition. So that's the trick, and that's what we are going to look at. So we are applying this oracle now. So the first qubit stays the same. And you see, I'm not doing this wrong. Okay. So, so the second qubit, it gets now the function value 0 added to it. So what was 0 becomes f of 0, and what was 1 becomes 1 plus f of 0. Okay, so this is what happens, and now what remains the same is that still we have 0 and 1 sitting here. Yeah? If this is 0, this is 1, and if this is 1, this is 0. So all that can happen is that this expression remains what it was, or 0 and 1 become interchanged. One of the two will happen, and that hinges on what f of 0 is. So we can rewrite this as -1 to f of 0 as a scalar prefactor 0 times 0 minus 1. Yeah, I give you a moment. Is that fine? Yeah, that's fine. So then let's do it for the other case, and I mean it's completely the same. So this is our starting state. So everything is the same, except we have now a different state in the first register, and so now what's being put up here is not f of 0 but f of 1. But in the end we get kind of the completely analogous result of what we had here, and this is, maps to now -1 to the power of f of 1. Yeah? Times 1 tensor 0 minus 1. Okay, good. Okay, so that alone doesn't give us too much, but what we now do is we said this earlier, we are querying this oracle in superposition. So far we haven't done it. Yeah, so far we either queried it for the input 0 or for the input 1. But we're now querying it for the superposition 0 plus 1 in the first qubit register. Yeah, so that's what we now do. And quantum mechanics is linear, so what's going to happen here is already given to us by what's happening here, by linearity. So we just have to kind of collect the terms.
So what we are getting here is minus 1 to f of 0, 0, plus f of 1, excuse me, minus 1 to the power f of 1, oh my god, I'm running out of space, 1 divided by square root of 2 tensor 0 minus 1 da 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 for the second qubit. Okay, good. So let me rewrite this expression a little bit. Minus 1 to the power f of 0. Now comes the first state, 0 plus minus 1 raised to the power of f of 1 minus f of 0, state 1, ta-da, tensor product with the second qubit, which is just a bystander in this calculation. So the important thing is here. Yeah? So regardless of what this difference of values is, this is an eigenstate of the Pauli operator sigma x. If this difference here of function values is 0, then you get the plus eigenstate, and if this difference here of values is 1, then you get the negative eigenvalue eigenstate of sigma x. So you measure in the x basis and figure out what this difference is. Yeah? So upon measurement of this first qubit in the x basis, you get this difference. And now that tells you about the nature of the function. If the difference is 0, then the function is constant, and if this difference is 1 modulo 2, then this function is balanced. Yeah? So you got this with one oracle call. Yeah? And so you have a difference between what you can do quantum mechanically and what you can do classically. It is only a point of principle. There is no application for this. Yeah? Okay. Good. Any questions about that? Not the case? Okay, so that's a good point to talk a little bit in general about what quantum computation is about. Quantum computation is not about what's computable. Everything you can compute on a quantum computer, you can compute on a classical computer, given enough memory and time. Yeah? And why is this so? I mean, what you can do is you simulate a quantum computer classically. I mean, you can write down the state of the quantum computer before and after every operation, so you can classically simulate it if you're not concerned about efficiency. So, yeah, quantum computing does not change what is computable. What quantum computation changes is what is computable efficiently. Yeah? And how is the efficiency defined? So efficiency is not in how many minutes or hours it takes. It is about scaling of the computational cost as a function of problem size. Yeah. So, I don't know. You want to calculate, I don't know, the ground state energy of the Heisenberg model as a function of the number of spins involved. Yeah. So this is a very complicated calculation. It becomes the more complicated the longer your spin chain is, or the larger your system is. And so you're asking, what is the computational cost as the function of problem size, which in that specific instance would be number of spins in the system. Yeah? So that is the question. Is this cost increasing polynomially with time, which is kind of rather weak dependence, or is it increasing exponentially with time, which is a very fast increase? And there are examples where quantum computation gets you from exponential or close to exponential to polynomial. And that's the kind of gain you can hope for in quantum computation. So this is what quantum computation is about. Just as a very general comment. Shor's factoring algorithm. So what it does, it breaks the RSA cryptosystem.
So the RSA crypto system is what you use when you make credit card payments. You go to the bakery, hand your bank card. There's an RSA transaction going on, and so if your friend or foe has a quantum computer, they can break this crypto system. So RSA, if people had working quantum computers, RSA would no longer be a secure cryptography scheme. And yeah, I want to put this a little bit in perspective. So it's not, of course, a very nice application, will not save mankind, but it is an application to be reckoned with. It is powerful. Yeah, so I think that's a significant step up from Deutsch's algorithm. So that's why I want to explain it. Okay, so let's put it into perspective. So this is cryptography. So you want to send messages secretly. And there's there's 4 boxes here, and they correspond to 2 quality parameters that we would want. And so one is security. And what we have here is non-conditional security. So there's kind of fundamentally no way to break it in theory. If used properly, of course there's human error, but if used properly, the schemes in this row, their security is unconditional. Yeah, it's just secure as long as you apply it properly. That's the strong form. So this is good. Sometimes people settle for something weaker, and that is the security rests on a computational assumption, namely that a certain problem, mathematical problem, is proven hard or conjectured to be hard, so that nobody in the world could solve it. Yeah? So such cryptography schemes exist, and our example RSA is one of those. So that's weaker, but maybe still worth considering. So this is one criterion. The other is whether the scheme is practical or requires very convoluted schemes. So practicability may be high or low. Yeah? And so let's talk about what's here, just to give you an example of what low practicability means. So this is the one-time pad. So the way you do it, so suppose you are a submarine captain and you want to send secure messages. So before you leave the harbor, you share with whomever you have to share it with, the person in the lighthouse, you share random bits. Very, very long string of random bits. And so then thereafter, you can send messages to the lighthouse that nobody can read. Namely, you have a certain message, phrase it in terms of bits, add the random bit string, send it out, everybody can read it, only the person in the lighthouse can decode it by, again, adding that random bit string, the string you shared. You have two copies of that bit string, so the person in the lighthouse can read your message. Until you run out of bit string. Yeah, then it gets, if you shortly before running out of bit string, you might use bit string twice that you have already used, and there begins the cryptography nightmare. Okay, so it is absolutely secure as long as used properly, but it's not very practical because you have to meet the person or have met the person before that you want to exchange information with. Good, but this thing exists, and therefore, so here the worst box inherits impracticability from one-time pad and also has diminished security. So this is the worst thing, and because there are better things, we never need to look at that. So this is the best, and quantum cryptography lives here. Quantum cryptography or quantum physics also provides a solution for cryptography, but that's not our subject here, but such things exist. Classically, you can have this and that. You can be perfectly secure, but impractical, or you can be highly practical, but the security resting on the computational assumption. So, and for bank transactions, people use this thing. Okay, and that is also something that a quantum computer can break. So you do not have this box.
I mean, you do not have RSA in the presence of quantum computers. And I want to talk a little bit about how this works. Okay, so here is the computational assumption of RSA. So you have an integer that is the product of two primes. And so the question is, for the eavesdropper, for the person who want to break this communication is, given n, what are the prime factors? And it is believed, not proven, but it's believed that this is a hard computational problem. If you want to get n out of these, is of course very, very easy, but the reverse is not. And so the best algorithm that is known, so yeah, so this is the number of digits in the number to factor. Yeah, and so the best algorithm that's known is almost exponential in the size of the number. Yeah, so it's yeah, it's not viable. Okay, but quantum mechanically, exponential changes the polynomial. In fact, I think quadratic. And so, yeah, that's feasible. So this quantum algorithm breaks the RSA scheme because given that, you can compute what the factors are. Why am I talking about that here? This is maybe not necessary for computational models, but this is one of the things that motivate quantum computation as a field as a whole. Yeah? And so when I asked you at the first lecture how familiar you are with the circuit model, some were not familiar, and so then you're probably also not familiar with Shor's algorithm, and I think I should say this once. So it is because of things like this, because of breaking RSA, that we think quantum computation has potential, and that's why we are looking at it. Yeah, in this course we're just looking at different things. This is a very general motivation for this course. Yeah, it's not something that you'll find in the exam. If there is an exam, we need to see about that. But yeah, it's just very general background information. And we do this because of things like that. Okay, so here's how it goes. Here's how the RSA protocol works. So there's two parties, A and B, and A wants to send information to B. And so here it's secretly, without other people listening in. And so the protocol starts with the receiver. The receiver picks two large primes, multiplies them, keeps the primes to themselves, but broadcasts the product. So the whole world can know it. It's not secret. So everybody knows this. And so now A, the other party, the party that wants to send something, uses this product to encrypt the message. So the message, say, is X, and Y is the encoded message, encoded version of the message, and this function from clear message to encoded message is facilitated by knowing this integer n. So again, A, the party, doesn't send anything in secret, it just broadcasts this encoded message to the whole world. And now, among this whole world is the receiver B, so the receiver B uses the two factors to decrypt the encoded message and gets back the clear message. So encoding gets by with the product, and decoding, however, requires the two factors separately. If you, yeah, okay. So now let's see what's public and what's private in this scheme. So public is the product of the two numbers P and Q, and the encoded message. Everybody can read that. Private is the clear message and the two factors themselves. Yeah? Okay, so what an eavesdropper would want to do is get from the public information N to the private information P and Q. And I mean, all that person would have to do is compute it, but that computation is hard. And that's what's protecting this cryptography scheme. However, if you have a quantum computer, then computing these private factors P and Q from this number is easy. Yeah, and once you have them, you can do what the intended receiver does. Namely, you can
use those factors to decode the messages.